Welcome to the workshop. Today we want to take a look at section 2.5, Mathematical Induction. This is our first proof method that we'll take a look at in this course. Now, you shouldn't let the idea of having to prove something scare you. It's really just, hey, we're going to give a justification for why we believe something is true. Except it's slightly better than why we believe, it's actually why it's true. So that's all that we're interested in doing here. It shouldn't be something that's complicated. It shouldn't be something that's, again, to be feared. So when it comes to mathematical induction, what we're interested in looking at or considering are statements that involve integers, essentially. And what we have, well, let's take a look at a few statements that involve integers to see what exactly we're talking about here. All right, so our first statement is that for all positive integers n, S of n is the statement. The sum of the odd integers from 1 to 2n minus 1 is n squared. So we're just looking at the sum of the odd integers, and we're saying what their sum is. Okay, it's nothing too crazy. So for example, we're looking at the numbers 1 plus 3 plus 5 plus 7 plus 9, but notice that 9 is 2 times 8. Actually, 2 times 4 plus 1, but I want 2 times 5 minus 1, right? This is 9. And so we're saying that this is actually 5 squared. So the sum of 1 plus 3 plus 5 plus 7 plus 9 is the same as 5 squared. Is that true? Well, 1 plus 3 is 4, plus 5 is 9, plus 7 is 16. 16 plus 9 is, hey, look at that, it's 25. It actually works out. So in this case, it's also possible to write S of n as the sum from I equals 1 to n of 2n minus 1. Okay, this is the collection of odd numbers from 1 to 2n minus 1, and summation notation says to add them together. And we're saying that this is equal to n squared. Okay, cool. So that's a statement involving integers, right? I go ahead and plug an integer in, and the statement is true. That's the idea. But we want to be able to prove that the statement is actually true. Okay, so the statement here is we have equality. Is it actually true? Yes, no, maybe. We saw that it is for 5, but what about the others? So here's another statement. For all integers greater than or equal to 4, S of n is the statement n factorial is greater than 2 to the n. So we could look at a specific example again. Now, a specific example is not a proof. It's just trying to help our understanding of what this statement is saying. So let's see, let's use, well, it's got to be greater than or equal to 4, so let's use 5. 5 factorial is equal to, let's see here, 5 times 4 times 3 times 2 times 1, which would be, let's see here, 120, yep. And then, let's see here, 2 to the 5th would be equal to, well, 2 squared is 4, and 2 cubed is 8, 2 to the 4th is 16, so 2 to the 5th is 32. And of course, we see that, yes, 120 is in fact greater than 32. So we can see that it's true for n equal to 5. So that's great. Cool. We want to know, is it true for all of the integers though? So we've shown it's true for 5. How would we show it's true for all of them? That's the question. That's what we want to do in this section. All right, so two more examples of statements involving integers. In this case, for all positive integers, the statement is that 3 to the 2n minus 1 is divisible by 8. Well, that seems a little crazy, doesn't it? Is it true? Maybe. Let's check it out a second. So let's go with n equal to 2. So 3 to the 2 times 2 minus 1 would be equal to 3 to the 4th, which is 81. 81 minus 1 is 80. And we're saying that it's divisible by 8. 80 is, in fact, 8 times 10. So yeah, it is divisible by 8 because I can write it as 8 times something. So that's awesome. We might also write our statement as S of n is that 3 to the 2n minus 1 is equal to 8 times k for some integer k. This makes it something, an equality that we can actually check. Makes it a little bit easier. And then for the last one, this is actually, I think, the fundamental theorem of arithmetic. For all integers greater than or equal to 2, the number is either prime or a product of primes. Pretty simple and straightforward. So most of these we'll be able to check by the end of the section. A through C, not a problem for the most part. Part D is a little bit different. That's something that might involve a little bit more than what we're interested in handling. But A, B, and C, yeah, we should be able to handle these by the end of the section. So how do we handle them? Well, we use what's called the principle of mathematical induction. So here's the idea. I'm going to try to explain it, just an idea, and then we'll read it. Let's say I know something is true, right? A statement about integers. Let's say that I know it's true for, like we had here, let's say I know that it's true for n equal to 5. Okay, now let's suppose I know that it's true for the next case. No matter where I'm at, let's say I know that it's true for the next case. Well, since it's true for 5, then since it's true for the next case, it'd be true for 6 as well. But again, we don't care where we're starting when we say the next case. So since it's true for 6, it'd be true for 7 too. And since it's true for 7, then it'd be true for 8, because this idea of always knowing it's true for the next step means we can always take one more step. Easy peasy. So that's the idea. We could go on forever. So it would be true for all integers. And that's what the principle of mathematical induction is. Once you start somewhere and you get that ball rolling, it's just going to keep rolling. All right. But we have to know that we can get the ball rolling. So we start somewhere, we get that place, we get the ball to the top of a hill, we go ahead and give it that push. Once we give it that push, we're all set to go. But we have to have it starting at the top of the hill, we have to have that place that we're starting, and we have to have the movement forward in order to get to go somewhere. So that's the idea of mathematical induction. So what is it formally? What are the details of it? Well, we need that place to start. So we need the statement to be true, right? The statement is true for the base case. The base case is called n sub 0 or n naught. So the n naught is the smallest case that we would want to consider, the smallest integer. So in our examples above, our base cases would be, for the first one, the smallest value of n that we could have is 1, because we're looking at all positive integers. So it can't be negative and it can't be 0. For the next example, our smallest possible value for n, our base case, would be n naught equal to, let's see here, 4. I want everything greater than or equal to 4. In the third case, again, we're actually looking at all positive integers, so it'd be 1. And then in the last case, it's for integers greater than or equal to 2. So our base case is when n is equal to 2. All right. So we have the base case, the smallest possible value of n is true. Okay. So all that we have to do is we have to verify that the statement is true. We verified it for 5 here. We verified it for 5 here. We verified it for 2 here. Okay, excellent. So we have a verification. Now, it's not going to work for 5. We need to check 1, and here we would need to check 4, and here we would actually need to check 1 again, because those are the smallest possible values. But that's all that we're doing. We're checking to make sure that it's possible. Okay. All right, let's see. So we need the base case. Once we have the base case, That's excellent. That gives us a place to start to get our ball rolling. Once the ball's rolling, we're good to go. It's going to keep rolling. But we need to get it rolling, and that's what this is. The second step says that whenever I have it true somewhere, I know it's true for the next thing. So I have a base case, and once I can get it moving, once I know it's true for the next thing, then it's going to keep going, and then we can say it's true for everything. So the second step, this step here, is called the inductive step. And what we do is we say if it's true somewhere along the line, no matter where we're at, right? If it's true here, then it's true at the next place, right? If we can verify that, if it's true here, then it's true there, right? Get that movement forward. If it's true at k and it's true at k plus 1, whenever it's true at k, that gives us our forward movement, and we can conclude that it's true for all integers. Okay, so base case and inductive step. So a proof by induction then, to show something is true by induction, all we have to do is identify what our statement is. Okay, what's our statement? Then we would say, all right, let's show the base case is true. Then we show that the inductive step holds, right? If we know that the base case holds and that the inductive step holds, then we know that it's true for all integers. So we just need to show these two things here. Show it's true for the base case, show it's always true for the next thing, and then, hey, if it's true here and it's always true for the next thing, we can just keep moving forward, keep moving forward, keep moving forward, and it's true for everything. So that's the idea of mathematical induction with the principle of mathematical induction. So we'll call it good there for now and take a look at several examples in this section and some more examples in the next section. So I'll see you guys back in the workshop for some examples of mathematical induction in just a little bit.